Hello, my name is Jim, and we're going to continue on with the next part of our power supply presentation. Last time we looked at a half-wave rectifier and some circuits and filtering and so forth, and it would be good to kind of know how a diode actually works. The diode uses a rectifier in our power supply, and it all begins in antiquity with Edison in the 1800s. And he built a light bulb and had some issues with blackening of the glass, and tried to insert a wire here to see if he could make that process stop. And that's because he was using a carbon filament at the time. So anyway, if you have a light bulb which is lit, what happens is it's very hot, and these are typically tungsten today, and electrons boil off the light bulb and cause what's called a space charge. And as an electron will go back into the filament, another one, because of thermal agitation, will exit. Now if we put a wire in here and make this plus, let me just put a big plus here, what will happen is these electrons, being negatively charged, will enter the wire and then return through some, say, external power supply to the circuit. So what we have is electron flow. We have to remember this now because we're in an electron flow in this direction. And if we reverse the battery, that would be, say, make this negative and this positive, is the wire will not emit anything because it's simply not hot enough to do it. So Edison didn't know it at the time, but basically what he did is he laid the groundwork for diodes. And to see a diode maybe from the late 40s, early 50s, looks like this. It's a vacuum tube. It has a red emitting filament. They wear out, so you have to change them. They're the most expensive part of a set, and to light the filament of this guy requires 5.5 watts. That has nothing to do with rectification itself. It's just the enabler. When the diode is conducting, you have power being lost in the I times V across the diode itself. So these guys get pretty hot, and they're very inefficient from the standpoint of green technology today. So let's jump ahead a little, well actually a whole lot, into the modern area where silicon is the standard bearer for electronic circuits. It used to be germanium, very, very temperature sensitive stuff, and this is much more robust. So what we know is that an atom is stable if it's one of its suborbitals, and what we're talking about here is the outer valence electrons is either half or completely full. And that's the case with silicon. So what we see with this guy, say, is these blue dots are electrons that belong to him, but he can share electrons from other silicon atoms around him, and those would be the green, so that this guy thinks, and excuse the human connection here, that he's got 8 electrons in orbital, and therefore this is a stable arrangement. So this is called a covalent bond, and it's sharing of electrons, and it is basically at 0 degrees Kelvin, it's a good insulator. Now, at temperatures above that, occasionally one of these electrons can get enough thermal energy to break free, and we'll be talking about that in a minute. So we're going to be talking about band gap, and this is a model, so it doesn't exist really. It's very, very complicated. But the way I look at band gap is being the distance between the valence band, and this is where the electrons are attracted by the nucleus, and the conduction band is where the electrons have enough energy to actually move through the circuit if there's an electric field applied. So we can consider the band gap to be the distance between the valence band and the conduction band. So if we take a look at a conductor, and we want to do the same for an insulator, is we find this very strange situation is where the valence band and the conduction band actually overlap. And a very good example of that is silver, specifically on a mirror. So if we were to be able to see this, is what we would see would be electrons kind of floating all over the place, not being tightly bound to any nucleus. So if we excite one of the electrons by hitting it with a light particle called a photon, it will increase energy, stay there for a while, return to normal, and re-emit that energy as a photon back toward us so we can actually see ourselves. So this is what it looks like for metals like silver and copper and so forth. Silver is an interesting material because it's oxide, and this is the dark stuff on spoons that they talk about, is at this time the only known oxide to conduct electricity. Copper, on the other hand, has an oxide which is greenish, and that's an excellent insulator. So every material has its own particular characteristics. Now let's look at insulators, and based upon the same thing, we have a valence band and a conduction band, except there's a large difference between them. And what that means is that we would have to add a lot of energy to take an electron and move it up into the conduction band. Now if we were to do that, we would be said to break down the insulation. And this could be, say, a piece of plastic on a wire or rubber on a rubber glove that's, you know, used by the electric companies to protect their employees. So the wider the distance, the better the insulator is. So silicon basically is an insulator, and thermal energy can sometimes move a valence electron into the conduction band, but this in its pure form is not what we're interested in making diodes. So silicon in itself, glass if you will, is a supercooled liquid. It flows. Church windows in Europe are a little bit thicker on the bottom than they are on the top because the glass has flowed over centuries. But to make this work for us, what we have to do is convert basically the insulation properties of silicon into that of a semiconductor. Not a good one, not an insulator, but somewhere in between, and we can control that by, say, voltage. So what we're going to do is we're going to dope this, and all that means is we're going to be adding impurities to it, and these are very, very sparse. It's very low percentage of impurities which are added, and the way that happens is that the silicon is heated from, say, 800 to 1100 degrees Celsius and exposed to a gas, and then the gas will diffuse down into the silicon, and the process folks know exactly how long and what concentrations and pressures and all of that to make semiconductors. So proceeding here, what we have is group 4, germanium and silicon, and these have 4 outside shell orbitals, which mean that it's capable of being stable. Then we have trivalent materials like boron, aluminum, and gallium, which have 3 valence electrons, and the missing guy, which isn't really missing, but it will be when we put it in with silicon, is going to end up being called a hole, which is an absence of an electron. Further, we have pentavalent group 5 materials like phosphorus, arsenic, and antimony, which have 5 outer valence electrons. We see this little blue guy here as being the 5th electron. It doesn't take much energy to move this guy along. Just like with this hole, it doesn't take much energy to move it along. So we kind of have to think of these holes as free-moving positive charges. And it's, I think, easier to think about electron movement than it is hole movement. So, here we have N-type silicon, and we have a donor in the center because it's donating a 5th electron, which is one of the groups that I just spoke to. And in this model here that I drew up, surrounded by 4 silicon atoms, and what you see in red are the electrons that associate with our donor, and the silicon atoms are covalently bonded, and then we have the 5th electron sitting out here, which is only of interest to our donor atom. Likewise, in p-type silicon, here we have a boron being an acceptor atom surrounded by 4 silicon atoms. This silicon atom isn't exactly happy because he's missing an electron to make 8 electrons in the outer shell. This one is happy, these silicons are happy, but this one isn't. So what this silicon atom would like to do is see the hole filled. And that would, of course, mean that the boron has 1 electron too many. So this is what we're starting out with here. And I've shown this as a 2-dimensional drawing, and it's anything but that. It's actually 3-dimensional, and the electrons do not orbit like the Earth orbits the Sun. That's a very simple model. They're found in, this is a nucleus, in 3-dimensional shapes, very weird shapes, all around the nucleus. And what is said is, if you go into the shape, you're more likely to find an electron than if you're not in the shape. So this is based on quantum mechanics, and we're doing a whole lot of injustice to it, but that's okay, because we can understand what we're doing. Also, while I'm here, I wanted to point this out. I came back to this before. I made this video before and erased it by mistake. But if you have, say, a load which requires 1.8 amperes, and you're thinking that, hey, all I got to do is parallel 2 1-amp diodes and I'm all set, I'm ending up with 10% safety error, a margin of safety for each diode. Not the case. If one of these heats up a little bit more, it tends to hog the current. And this current can actually be over 1 ampere, which will destroy this device. So if you're going to put diodes in parallel, you have to be kind of careful. Basically, buy a bigger diode, but if you have to, swap it out with a resistor, which tends to keep the current through each branch of this constant. So now we're going to take our N and P type material and join them together. This is anything but true, but for our purposes it'll work. Notice the symbol here, and when we join them together, what happens is that the excess electrons, the 5th electron, feel the hole on the P side and cross over and fill the holes. And what that means is, by the junction here where these two are joined, we have a plus-minus charge. Now, if we want to have current flowing, what we have to do is provide an external source of potential that can overcome this barrier, because this is a barrier that's basically stopping current flow. So what we want to do is come up with forward bias, and the whole purpose of that, if we want current to flow through the diode, is to overcome this barrier blockage. So this is a little bit of a busy drawing, and it's kind of hard to explain, but this is shown as a forward bias connection, and do note that this is electron current, not conventional current. And what happens more or less simultaneously, like I can't draw that, is that in a p-type, an electron will leave and go into a wire, then an electron in this p-type will leave and fill this hole, leaving an exposed hole here. And then an electron from this guy will fill this hole, leaving an exposed hole here. And then an electron from here will fill the exposed hole here. And since this electron already shed its, this atom, since it already shed its electron to produce the barrier voltage, now can receive another electron from the guy next to him. So he's going to come in, and for this donor atom, replace that 5th electron, which eventually, of course, is going to end up going across the junction and filling a hole. So what we have here is that electrons are repelled by the negative side of the battery toward the junction, and holes, again treating them as free-moving positive charges, are repelled by the positive side of the battery toward the junction. So electrons are moving this way, and holes are moving this way, and when they get in the area of the junction, they recombine An electron will leave and an electron will enter. So holes in electrons move in different directions, and when we have an electron fill a hole, this is called recombination. Now, how much voltage and current? And that depends upon Schottely's equation that we discussed the other day. Now let's put our PN junction under reverse bias. Unfortunately, this is a whole lot easier to understand. So I've turned the battery around, and the N-type with all those loosely bound fifth electrons are now attracted to the positive terminal of the battery, and contrarily, the holes, which we're treating as free moving positive charges, are attracted to the negative side of the battery. Now, what to note here is that the area around the junction is devoid of any carriers, hence no current flows. Electrons and holes are not being forced together, they're being pulled apart, and this is in fact an insulator. As a matter of fact, it sometimes uses a variable capacitor, but we're not interested in that in industrial electronics. So in reverse bias, basically the only thing that's going to flow through this are electron-hole pairs which are created by thermal agitation. So basically what we're going to say is that the device is off, excepting for this leakage, and this is called a depletion zone because it's depleted of carriers. Now, reverse breakdown, and this is reverse bias to the extreme, means that the voltage is so much, and here we're looking at the depletion region, is the electric field is strong enough to take an electron in our silicon atom and rip him out of orbit. Rip, not exactly the right word. So this electron goes zipping by this guy and passes a little bit of energy along to this electron, which is also stressed, so he breaks free, and what we end up with is a pebble at the top of the hill turning into huge boulders at the bottom of the hill. So if we were to look at that, what we would see is that in a forward direction we have the standard equation, which we talked about the other day, and in a reverse direction we're going to reach a point where we start to cause an avalanche or a breakdown. This is called the PRV, peak reverse voltage, or PIV, peak inverse voltage. Now we have to be careful of this because if we're not designing a special kind of circuit, this is almost always bad because we're dealing with a high voltage, a high current equals a high power equals bang. So certain diodes are designed to work in this region, and those are called Zener diodes or avalanche diodes, and there's actually two different mechanisms that work here, but whatever. And it's just that the device has to be operated in the safe zone, and that's where the power dissipation of the package is such that it can get rid of the heat. And as you can guess, it's going to be a relatively stable voltage point based on the PRV, which is controlled and manufactured. So these can be used as voltage regulators. Are they? Not so much today, because there are better ways of doing it. But anyway, this only happens under reverse bias where we break that down. Now, before we leave the topic, and this basically covers it for diode operation, is let's just talk a little bit about a light emitting diode. And the purpose of a LED is not to rectify, it's to emit light. So, light emitting diodes are not made with silicon, they're made with trivalent and pentavalent materials, 3,5 materials. And what will happen is we have the valence band and the conduction band, and if we apply a voltage to that, we can add enough energy that it moves into the conduction band. Now, once we have an electron up there, it's not going to stay up there forever. He has to return to the valence band, but the energy has to be accounted for. So this cannot leak energy. So what will happen is that the energy will be released in the form of a photon. Now, a photon is a light particle with wave characteristics, or it's a wave with particle characteristics. Not easy to understand. Now, the distance between this can be made to be varied, so can the energy of the photon that's released. And the equation for that is the energy equals Planck's constant times the frequency, believe it or not. So what that says is that if this band gap is far apart, we're going to end up with a high energy photon like violet or blue. And if it's closer together, we're going to emit a photon of less energy like red. And if it's still closer together, we're going to emit a photon of energy, say, of infrared light, like what we use to control our TV sets. If we go lower yet, we're able to see thermal imaging, and lower yet is we're in the upper spectrum of radio waves. So there's a whole continuum between radio waves, 1000 hertz coming out of our generators, all the way up to light, going further into ultraviolet, X-rays, cosmic rays. All of this has to do with the energy associated with that photon. Now, ultraviolet light and anything with more energy is considered to be dangerous because these photons have enough energy to penetrate our skin and alter the DNA, which can lead to disease. So we kind of have to watch our exposure to high energy photons. And that's kind of the basics of light emitting diodes, and the gap is controlled by using different substances inside of it. Now before I leave this, white is a combination of colors, and if we want to have a white LED outside of our television sets in Jumbotron, where white is made by the addition of red, green, and blue, typical light emitting diodes for residential are made with blue emitters. They're actually high-powered blue LEDs which have broad emitting phosphor on top of them emitting yellow. And that tricks our eye into thinking that it's white. So the more yellow phosphor, the more, I'm going to call it friendly the light is, the warmer the light is. And warm light is about 2800 Kelvin. So if you took a black body and heated it to that temperature, it would be the same as a warm light bulb. If they add less yellow phosphor, as the color temperature goes up and the light takes on a harsher characteristic, like 5000 Kelvin. Now a lot of people find that they can read easier with this kind of color of light, called reveal light bulbs in the incandescent world. So the color temperature is controlled by doping yellow phosphor on a blue emitter, and these can be quite bright. I could go on from there and talk about color rendering index, but it kind of bothers me because I think people are being ripped off by it. CRI basically means that your red apples in your fruit basket aren't going to seem so red if you don't use a certain type of light emitting diode. But we'll end it there, and that'll do it. Thank you for watching.